Look at that. That tells the whole story right there.
I am a believer.
But what actually made the ice go boom? The truth is, no one really knows.
So we are ready to make history?
Speculating that heat from the burning thermite is decomposing the water into hydrogen and oxygen, which in the presence of a source of ignition, namely hot thermite, is exploding. Now, I sort of have a problem with that because that requires that a whole bunch of hydrogen and oxygen be instantaneously created, and I don't know that that's possible. We don't know. It's a mystery, but one way or another, that was a heck of a bang.
So what did make the thermite go bang? Because in principle, all that you have here is liquid iron and ice. Well, clever ideas are frequently not clever because they're so complicated, but because they're so simple. And in this case, boy, is it simple. And yet, it still has just been published in one of the world's top scientific journals, Nature Chemistry. It's a simple idea that could shake the world, either literally or maybe metaphorically. It's always kind of difficult to tell with new scientific discoveries, but I can tell you with certainty that this work will save lives. However, what really makes this research unique is that it was started right here on YouTube, with almost every stage of the research resulting in a spin-off video of one sort or another, and it was initially all done with crowdfunding of one sort or another. And damn straight that made it into the acknowledgement of the paper. Now, many who watch a reaction like this will just shrug with indifference. That's just the alkali metals reacting with water. It's been known about for about 100 years. It's obvious high school chemistry. And that's what it's done in high school. There's nothing of any great interest here. Well, I'll be honest. That's what I thought too when I first ordered some sodium and potassium and a couple of consumer-grade high-speed cameras back in 2011. Sure, it was all well understood, and there wouldn't be any really interesting scientific discoveries that would come out of it, but whatever, it would still be really cool to look at one of these explosions in slow motion. Problem was that from almost the first time I looked at this with a thousandth of a second resolution, there were green gases, blue colours, and explosions taking place below the millisecond timescale, none of which had any right to be there at all. It was bloody clear that there was something very, very strange going on here. And nothing arouses the curiosity of a scientist more than something they don't understand. Especially when the established view says that it's all terribly well understood.
That reactions between molten metals and water are very well studied. There are a whole series of papers. I've got one here which Brady likes. First of all, because it's from the journal Nature. The reason he likes it is it's from 1973, 3 years before he was born.
So if they think this is all terribly well understood, how do they think this is happening?
There is quite a well-known effect known as a fuel-coolant interaction, where a molten metal drops, say, into water and causes an explosion. And we've sort of had some of those in some of our videos with cesium and sodium in water. Imagine you have liquid sodium, the melting point is 96 degrees Celsius or centigrade, however you like to say it, and which is very close to the boiling point of water. And of course, it could have been hotter than 96 degrees, so when the water goes in, it may well be in an environment that is higher than its boiling point. And if you look carefully, first of all, the reaction blows upwards, presumably going through the hole that the water's made going in.
Now, to me, that just instantly didn't sit right, because these things, they really go bang. But maybe the most convincing argument that it's not this is aluminium. Now, it turns out if you get aluminium, you can heat it up with a gas torch well over 1,000 degrees to the point where it's white hot, and you can still hold it by its oxide skin, and then you can dump it into water. And on this scale, far from leading to a thermal explosion, all that happens is the metal locally boils the water that keeps the aluminium and the water separate. And the same thing happens if you just drop the metal into water. You see, the fundamental problem is all things that go bang do so because of a sudden expansion of gas. Well, actually, now let me take a step back here. The actual reaction that we're looking at here is the alkali metals, that's lithium, sodium, potassium, rubidium, and cesium, with water. The general form of this reaction is you get the alkali metal plus water, and that gives you the alkali hydroxide and hydrogen. And this reaction can only take place when the metal and the water are in direct contact. Hydrogen gas, of course, can burn in our atmosphere. Indeed, when mixed with air, it can give some pretty reasonable explosions. And so, well, could that be what we're looking at here? Well, these experiments were done very early on to give me some idea of the sort of explosions that you could expect by the hydrogen given off by this reaction alone. Yeah, damn straight know your hazards, even if they're expertly done with milk jugs and cheesy puff containers. But joking aside, that is actually legitimately why this was done, because if you're going to operate in a hazardous environment, you must know the hazards that you may encounter and do what you can to minimize the hazards. It is just common sense. As the old saying goes, the secret to a long life is to try not to shorten it. I know, says the guy doing the crazy ass explosions, but whatever. However, in the end, none of that really mattered, because even though there's this potentially explosive nature of the hydrogen-air mixture, that's not important, because with another expertly constructed piece of apparatus made from a juice jug and some knitting needles, that is this kit designed to rapidly immerse potassium in water and have it localized in a specific place, you can see that the metal explodes even when it's completely submerged in water. There is no oxygen there for the hydrogen to burn in. That is, the combustion of hydrogen is not a significant contributor to these explosions that are witnessed between alkali metals and water. Indeed, this shot's beautiful because you can later see the hydrogen flashing off later. Now at that point, the intrigue levels go through the roof. You see, you've got a metal as a solid lump here, and it's in contact with water, which is a liquid. And the two can only react on the interface, and when they do, they make sodium hydroxide and hydrogen, both of which will serve to tend to keep the alkali metal and the water separate. That is, the reaction that happens here should inhibit further reaction. And for an explosion with a heterogeneous reaction like this, you need the reaction to actually promote further reaction, not to inhibit it. This explosion should never happen. And I can't tell you how many hours I've spent going through this sort of thing, frame by frame, staring in disbelief at what I'm looking at, just shouting at my screen, that's not possible. You see, the best I could come up with was a Coulombic explosion. Now, all explosions follow a sort of exponential mathematics. That is when a reaction occurs, it has a certain probability of stimulating another reaction. And in order for an explosion to ensue, you need one reaction to stimulate at least one more reaction. And so this is the thing, when you've got the sodium and the water, the reaction that takes place actually inhibits further reaction by creating gas on the interface that separates the two reagents. That is, it inhibits the reaction. It's the opposite of what you need for an explosion or a detonation. However, it's when you start drawing it like this that you realize that when you get this reaction on the surface, you've actually sown the seeds for a Coulombic explosion. Look, when you start, you have the sodium ions here stabilized by the conduction band of electrons. And when you get a good strong contact between these two, the electrons shuffle over and give you hydrogen atoms and hydroxides. So now all of a sudden you've got all of these sodium ions next to each other without the stabilizing electrons, and on the other side you've got all of these hydroxides, all these negatively charged ions next to each other. Now the sodium and the hydroxide ions being together, that's not a problem. But having all of those sodium ions next to each other, that's a big problem. They're going to move apart. And when they do that, they sort of create almost this, they create a new surface. And not only that, they create this sort of conveyor belt type structure that allows both of these reagents to come together. You have this positive feedback mechanism that allows this heterogeneous reaction, this exponential mixing. And therefore, you have the potential for an explosion. Problem is, that's a cute idea. But that's not enough, because cute ideas can be completely wrong. And at that point, the project kind of went professional. and it went from using a $300 camera to one that cost about $100,000, and from one curious geek to a team of gung-ho scientists and a project involving a couple of research institutes and supercomputers. But the first experiments we did were still infuriating. We constantly found it almost impossible to get a clear view of what was actually happening. You see, the problem is when you put the alkali metals into water, they tend to fizz around on the surface for a bit, moving around all over the place, and then at some random point later, it explodes. And the problem was, for us to get this really nice image, we needed the camera zoomed right in, right up close to the action, which basically meant your chances of having this random fizzing drop explode right in the middle of the field of view were pretty small. Further, if you used a small vessel, what tended to happen is it would generate lots of little bubbles which would obscure the view of what was happening. And finally, this reaction was bloody dangerous.
Yes! Oh! The water is 25 degrees. Okay?
Yeah.
And just so we're clear on how violent and erratic this explosion can be, this was merely 350 milligrams of sodium. That's only about the size of an aspirin tablet.
This time you missed to take
Yeah, I missed the take with both. Normally we have this one and a little high-speed camera going, but that is all that's left of our conical flask. That was only 350 milligrams as well.
What was really needed here was a way of getting the alkali metals to explode in exactly the right place at exactly the right time. Now, because these reactions seem to have a tipping point, and if you get past that tipping point, you get a boom, and if you don't get past that tipping point, it just harmlessly fizzes around on the surface. I'd long had this deep, but difficult to demonstrate suspicion that these explosions were linked to having a really nice clean metal surface in contact with the water. And that's a big problem, because these metals typically come in this goopy oil that coats the surface, and even if you wash most of it off first, you're still dealing with surfaces. You only need a very small amount to cause lots of problems. Secondly, if you cut the metal, that's great for generating a new surface, but it oxidizes very quickly in the atmosphere. So, the first idea involves getting a freshly cut piece of potassium and putting it on the end of a needle glued to a Nerf gun and firing it into water.
Rolling. Okay.
So where do you go?
Yes, that's research-grade science being done there with a remote-controlled car used to remotely fire a Nerf gun. And that worked. It exploded almost on contact and in almost the right place. But it turned out we could do much better. You see, by pure chance, when I first got my sodium and potassium many moons ago, one of the first things I did was try and make some sodium and potassium alloy, because it's just one of those really cool things. You take sodium, which is a solid metal, and potassium, which is a solid metal, and you mix the two, and ka-ching, you get a liquid metal. And that liquid metal also happens to be one of the coolants they use in some nuclear reactors. Now, it also turns out that whilst I was trying to get rid of some of this stuff, I found out that if you put it in hexane and added 1 or 2 drops of isopropanol, that's rubbing alcohol, you could get this immaculately clean metal surface, beautifully clean, mirror shiny. And that's just the thing that you would need if the alkali metal water explosion is driven by a clean metal surface. Even the very first results were fantastic.
I'm glad I had the face shield on that.
Click my sound, I'm not sure it's not good. It's excellent.
And the beauty is you can handle the sodium-potassium alloy in syringes and it produces a drop of a characteristic size. And you can vary the impact speed of the drop just by varying the height you drop it from. This is where it really came together. You see, if you drop the sodium-potassium alloy down a 1 meter drop under an argon atmosphere to stop any oxidation of the metal, it explodes essentially 100% of the time. and as close to the aim point as you can align it. Which turns out, if you're willing to drill some holes in the roof of your lab and to commandeer some optical beam support, is pretty bloody good. And big props to our German collaborators for being heroic enough. And yes, I really do think that heroic is the right word for being willing to take these risks with their lab and their camera to make this work come together. See, the best thing about this setup is it's almost entirely safe, to the point where one drop of sodium-potassium alloy reproducibly makes a drop about 6 millimeters in diameter and weighing about 1/10 of a gram. And that explodes essentially 100% of the time, and further, if you use this argon atmosphere, there are no secondary explosions. It utterly transformed this study from one that was erratic and dangerous to one that was exceptionally contained and reproducible. The results are impressive. Here, filmed at 10,000 frames per second, that's 1/10 of a millisecond per frame. The whole reaction is over before it's even started. However, if you stop and go through it frame by frame, not much happens, and then in 1/10,000th of a second, the drop turns into a hedgehog. And this is really all you need to know, because from there, the rest writes itself. There is no gas generation driving these fingers. These metal fingers are accelerating into the water, and that acceleration is impressive. I mean, this drop's about 5 millimeters across, so you can get a rough idea of the acceleration from comparing this frame to this frame. It's accelerated to about 1/10 of the speed of sound in 1/10,000th of a second. Keep up that acceleration for merely 1 second, you would have escape velocity from the Earth. And after these fingers have injected themselves into the water, you just get this regular expansion of the hydrogen created by the reaction of the alkali metal with the water. But that's all you need to know. The metal is accelerating into the water. And if the metal is accelerating into the water, then there is a force driving it. That's just Newton's second law of motion. And all you have to explain that acceleration is the metal and the water. And almost the only thing that will fit there is the Coulombic explosion. But we got more than the experiments, because we had a talented computational chemist on the team who did some calculations on this. And so we have these quantum simulations that show that the transfer of the electrons from the surface of the metal to the water takes place in picoseconds. That's about 1/millionth of a second. And you can add some molecular dynamics calculations, making some best guess approximations, but the results all point to the same thing. And even some calculations based on some equations left to us by Lord Rayleigh all point to this being a coulombically driven explosion. The electrons transfer from the metal to the water, and that leads to a attraction between the positive and negative charges, but repulsion everywhere else. Having all of those negative and all of those positive charges next to each other is very bad, and they move apart, and as they do, they generate more surface. And once that repulsive force is equal to the surface tension, that's it. That's the tipping point. That's when you get the boom. Indeed, maybe it's a fascinating example of what negative surface tension would look like. But as the expansion of the surface generates more surface, you fulfill the key criticality requirement for an explosion between two macroscopically separated reagents like this. But I hear some say, okay, so that's a nominally interesting explanation for why sodium explodes in water. But fundamentally, it's still just sodium exploding in water. I just don't see how that can possibly change anything. Well, it's always difficult to say with something like this. But it is a completely new form of a real boom-boom type explosion, or more exactly, a new understanding of why the boom-boom reaction happens. But how this knowledge could save lives is quite simple. Metal water explosions are a common killer in foundries, and when the water reacts with the actual molten metal in the molds, those explosions can be devastating. And knowing how to suppress them could be a lifesaver. So based on our understanding of these reactions, we worked out that if you add something that sticks to the surface of the water, that would make it harder for the reaction to reach this criticality, and it would suppress the explosion. And we found out that by merely adding 5 parts per thousand of hexanol, essentially a sort of weak surfactant, this transformed the nature of the reaction of these metals with water from one that essentially exploded 100% of the time to one where it almost never exploded on contact with water.
Okay, we're almost ready. Okay. That looks beautiful.
And that's kind of a useful thing to know. But things like this are just the obvious applications. The potential of this new technology is clear if you just take a look at the simple ballpark numbers for this reaction. So if I take, say, 1 kilo of sodium, that's about the volume of a 1 litre pop bottle. And let's say that explodes in water in, let's say, a millisecond. The rate of electron transfer from the metal to the water clocks in at about 1 billion amps. There is nothing that comes close to this rate of electron transfer on the Earth. We're almost getting up to the level of 1 million times the current that you get in a lightning bolt. The rate of surface expansion is phenomenal. A litre of sodium has about the surface area of a sheet of A4 paper or just a piece of letter paper. If that explodes in about a millisecond, that means that the surface area of that litre expands to something about the size of a small town in 1,000th of a second. Yeah, it's likely that these reactions will have some very interesting electronic and nanoscopic properties. And that's not just blowing smoke, because there's something else about these reactions that no one seems to have noticed and something that shouldn't be there. Principal problem is there just aren't that many ways where you can get really close to an explosion like this, one which is releasing a comparable amount of energy to TNT exploding weight for weight, and where you can actually measure something useful, some unique property that is only there for about 1/10,000th of a second. But maybe the most incredible thing here is if you just look around on YouTube, where I actually did a lot of the background checking for this stuff, it's so obvious. It's nothing or boom. It's nothing or boom. Nothing or boom. You get lectures on this from the Royal Society. You even get rooms full of university lecturers looking directly at alkali metal explosions with a high-speed camera. All of them functioning on the presumption that this is all well understood and that there is nothing new to see here. Not one of them took the step back to say, that's not possible. That just shouldn't happen. But in the 4 years or so since I first looked at this stuff, there's just something to do with some consumer-grade high-speed cameras. Not only has this been an immense amount of fun, I've got real fond memories of distilling cesium on the barbecue on our institute's balcony. But what really makes this work unique is that it was started on YouTube via crowdfunding. And these experiments on the cistern of my toilet, or in the gorge behind my apartment, or on the high plains of the Sierra Nevada played critical roles in how our ideas developed. And while the end game that really did take this to the hoop required 2 institutes, 2 group leaders, half a dozen or so authors, each one of which played a critical role, it must be said that there are few instances in science where you can point back to the exact moment before any of this was known and say, that was the point, that's where it all began. But while it might be where it began, this is not where it ends. Because let me tell you, there is so much more to this reaction than meets the eye. And honestly, for every one thing that we understand here, there are 10 that we don't. Just for a taster, watch the Invisible Metal video. I've not got a clue what's going on there. And therein lies the game. Because nothing arouses the curiosity of a scientist more than something he just doesn't understand.